And I think our following speaker, I don't think he needs a lot of introduction yet. We all know Gilles after a few days. Gilles is not only the chair of LASSI. In his daily life, he's of course also a researcher on land subsidence, primarily TISOLS. And he does that affiliated to the Taurus Research Institute and Utrecht University. And he's going to talk about the relation between land subsidence and carbon dioxide emissions from peatlands.
Yes, thanks very much. Yeah, good afternoon, morning still. I'm giving this talk together with my co-author, Erkens and Van Asselen. It's a different twist than the abstract or paper that we wrote, because I'm going to use a case study to make the point, instead of just making the point as we did in the paper. And the point is that if you can use land subsidence to calculate the amount of CO2 respiration, and vice versa, and we have done that in the past, but there are two important elements that you need to realize. One of them is which part of land subsidence is related to the decomposition of peat, because that is causing the CO2 respiration. And the other one is that you need to have a certain conversion factor to go from volume to mass, because CO2 respiration is a mass, and of course land subsidence is a volume. Oh, that was too quick. So yeah, that's hardly needs any introduction anymore, but we're going to focus with this case study on the Netherlands, on the last 1,000 years of land subsidence. You have seen this map in the opening day, and this map is going to be one of the products of this talk, or mentioned in this talk. And of course, on the left, you can see what we had in the last 1,000 years. We drained the peatlands 1,000 years ago. That led to lower ground levels, but also led to subsidence. So in due time, the ground level was lowered towards the ground level, and that meant that the world became too wet. So we had to lower these ground levels again, which again caused land subsidence. And this happened over and over again, as you can see in this spiral. And in the end, we had 1,000 years of land subsidence in the peatlands. Again, too quick. So we have a lot of peat in the Netherlands. This is a map from Peter Vos showing the amount of peat that we had just before the cultivation of the peatlands. So let's say 1,200 years ago. Everything that's in brown in the west and in the north of the country, here, that's all peat. And we're currently somewhere, if I'm able to do it exact, somewhere here in Delft in the peatlands. And what's important with peatlands is that they grow, of course, in open water. So they tend to fill in open water bodies, as you can see in the image here. So it starts with open water, and then from the sides you have this peat growth. But the very important stage is here in the end. Some peat forms are capable of forming above the regional groundwater level. So they have a positive topography, and we call these peat domes or bogs. They are about 2 to 3 meters above sea level. And at the sides, then you can have peat fens, which are, let's say, 0.5 meter to 1 meter above sea level. So it's important to remember that before we start to cultivate these peatlands, they were above sea level. They were never below sea level. So not even the Dutch, we started below sea level. We also started above sea level. And that there were two things that we did. We drained them and we excavated them. So excavation we did either in the wet, as we say, so under submerged conditions, or dried, and then we cut the peat here. We dried the peat and we use it in stoves for combustion for heating purposes. So that's burned. Drainage that happened for instance, from the Bishop of Utrecht was a large initiator of that. From the rivers or from canals, we drained the peatlands from both sides, basically cutting ditches and canals to lower the ground level to make them arable. And this is what happened over time. You can see here a cross-section with a creek, 900 after Christ, so 1100 years ago. There is a peat dome here at the right. That's higher, so that's 2 meters above sea level. And because we drained it, slowly land subsidence started, and now currently the whole topography is reversed. So the creek is still at the same level, maybe increase a little bit even. And here the dome is at a much lower level, so we have a reversed landscape. And what's very important, of course, that one of the important processes that cause this is decomposition of peat. And you can see this in the photo here. This black part of the peat core, that's where oxygen was able to be to go into the peat and allowed for decomposition or cause deposition. That's causing a part of the land subsidence. The brown peat below that is not being affected by oxygen or by decomposition and is still in its original state. Now, that's not the only process that leads to land subsidence. There's also compaction, so consolidation and creep, of course, happening. So we need to be able to separate these two processes because it's only decomposition that causes volume loss and CO2 respiration. So if we want to combine the two, we need to be sure that we can separate the two processes. So this talk is about 1,000 years of land subsidence and how can we calculate how much CO2 respiration did we have over this last 1,000 years. We lost a lot of peat, but we have to be able to calculate the amount of CO2 respired. And as said, there are two challenges. We need to isolate the peat decomposition from the other processes that lead to land subsidence, and we need to be able to convert a volume to a mass. That's very important. So that's the two steps I will follow here. And it's not just this talk that we do this, but we do this more often. The official reporting of the Netherlands to IPCC on CO2 emissions is based on land subsidence rates. And Jan van der Akker, sitting in the room, has been working on that. So we use land subsidence a lot as a proxy, and we're also now trying to do the opposite, using CO2 respiration rates to calculate land subsidence. So it's very important that we have this mechanism straight and this way of the relationship. So, to the research, this is a simplified cross-section of the Netherlands. In the east, here the Pleistocene uplands. Here in the west, the sea and the dune area, and in between, I'm now oversimplifying, but for the talk it's okay. There's the peat area, that's in brown. There is some clay deposited. And if we want to know how much land subsidence we had over 1,000 years, we just need to know the present surface and the surface of 1,000 years ago. And if you subtract these two, then we can calculate the volume lost. Now, the present surface is not a big problem, of course. The surface of 1,000 years ago is slightly more challenging, but doable. And you can see we had these peat domes, which were a couple of meters above sea level. And then here, these are the fens, which were a couple of decimeters above sea level. So that was the landscape. So the peat domes, they're largely gone because of excavation. So they're now the deepest part of the landscape. And the fens were largely, and part of the box as well, they were largely drained. So the difference is the volume that we need. And an important presumption is in all of this that all land that's presently elevated under mean sea level used to be elevated at or above, right? So that's the assumption that we make. Now to the left you can see a map of a reconstruction. We used an older reconstruction and improved it a little bit of the extent of peat domes and peat fens 1,000 years ago. So everything in dark brown are the peat domes, as said, a couple of meters above sea level, and in light brown are the peat fens. So we could attribute an elevation to that, and then we could also, we have the laser altimetry elevation of the Netherlands, a map on the right, showing that most of the same area is now below sea level. You can see some areas, the deep blue areas, those are the areas where the former peat mines were located, where peat was excavated. So we have these two elevations, and we can just subtract them. And that's basically gave us the map that you've seen before. So that's the 1,000 years of land subsidence, 1,000 years of volume loss that we had. So just some fun facts. It's 2 meters on average, so 2 millimeters per year over 1,000 years, land subsidence. Maximum is about 8 to 10 meters in one of those peat domes. And the total volume lost was 20 cubic kilometers. So 1 by 1 by 1 kilometer, and then that times 20. And the results are, this has been mentioned before, but it's a large part of the coastal plain is now below sea level. We need 24/7 pumping, and we have reversal of some drainage systems that completely changed as a result. But if you look at this map, you can see there are two groups of land subsidence. You have a larger part which is about 1 or 2 meters has subsided, which is this peak here. Should do it like this. This group, and there is a smaller group that subsided about 5 to 6 meters. So those are the 5 to 6 meters are the mines, the peat mines, the former peat mines, and the other ones are the large piece of land that has to do with where land subsidence has to do with drainage. Okay, now we go to the, now we know the volume. Now we want to convert this to CO2. So we need to make sure that we get rid of all the other processes to isolate those processes that led to CO2 emission. Well, here there are three process components that led to the volume loss. And the first one is very easy because combustion, putting it in a stove, directly leads to CO2 respiration, right? So everything that is combusted or used for in the mines, dug away in the mines, that we can convert that to CO2. The second one is erosion of ditch bank after peat digging. That happened quite a lot. For those from the Netherlands, the Haarlemmermeer is a great example of this. But it's only 2% of the area, so we didn't put too much effort in this. It's also questionable if this is a direct human impact or an indirect, and that was important for us, so we leave that out for the moment. And then the third one, of course, is drainage, and that leads to shrinkage, compaction, which I now combine consolidation and creep, and oxidation. And we're after the oxidation part, so that will be a more complex element. But let's first go to this combustion. So we mapped out all the former peat mines in the Netherlands. You can see it's quite a lot. We did quite a lot of mining. And in area, there are only 15% of the coastal peatlands, but and the other 85% is drained. But in volume, they're very deep, these mines, as we've seen. In volume, they compose 1/3 of the lost volume of 20 cubic kilometers is due to the mining, and the other 2/3 is because of drainage. So this 1/3 we can directly convert to CO2, and we'll come back to that later. Now we go to the drainage, and we have shrinkage, compaction, and oxidation. Now shrinkage is relatively easy as well. That happens above the ground level in the unsaturated zone. But everything that has shrunk over time also oxidized later. On these timescales, if you think of 1,000 years, you can combine that into one single factor. So even if it has had land subsidence, it caused land subsidence earlier than it did when it respired, in the end it's all the same process. So shrinkage we can ignore for now, but there still is the compaction. So we need to isolate the compaction from the oxidation here. And then this is, it's actually a byproduct of a paper that Michiel and I wrote a couple of years ago, but it's one of the most interesting figures. I like it a lot, but maybe that's just me. Let's see if you like it as well. It shows the relation between the relative amount of organic matter content in the Dutch peats. You can see the samples which were taken all over the coastal plain in the Netherlands against the organic matter density. Now, there are two important things. First of all, for your convenience, I colored the clay and sand samples, which have some organic matter but are not peat, gray. So those are the gray dots. So there's less than 20% relative organic matter. So we focus now on the brown colored dots, which are the peat samples. Now they show no trend with organic matter density. There's a wide range, but there's no trend. That means it doesn't matter how peaty the sample is, how much organic material there is, but there is always a certain limit to the organic matter density. So the density depends on, for instance, the compaction history, but not on the specific peat type or if it's more or less peaty. There is a relationship, however, between the more clayey samples. For the more clay samples, there's a relationship between the relative organic matter content and the organic matter density. So the good thing about this, the easy thing is, even though we have a wide range, that we can have an average organic matter density for all peat samples in the Netherlands, which is the average one is 103 kilograms per cubic meter. We have a wide range with a lower boundary of 80 and an upper boundary of 150, but there is within this range, all the peat samples, the organic matter density is available. So we solved the problem here of going from volume to mass. But the next step is that we need to understand how much compaction happened here. We can also use these samples with this organic matter density to compare them with a very easy compaction model to freshly formed peat. And then we get this figure here. So this shows the amount of the organic matter density is now on the horizontal axis. So it used to be on the vertical axis, but now on the horizontal axis. And this is the amount of consolidation. So this shows how much consolidation would I need to get to a certain organic matter density. And we would never be able to reach, or if we would reach the average organic matter density of 103 kilograms per cubic meter in the Netherlands, that means that we would have had 28% of consolidation, about, there is of course a range, but about, to achieve that, compared to freshly formed peats. We can also see that the lower boundary, we need only 7 or so percent of, if we take 80 kilograms per cubic meter, and if we take the upper boundary of 150, we need 50%. So that's the range, the average range of compaction of all those peat samples in the Netherlands. Now, I'll take the average, that's for now, to go to the final calculation. So we now know that 28% of the volume loss that we had, and that was 2/3 of the 20 cubic kilometers, I hope you're still with me, that is attributed to compaction, and the rest is oxidation. So we can use that number and add together the combustion-related 1/3 loss of the 20 cubic kilometers to get to the total emission. And that's then 0.83 gigatons of soil carbon that has been lost from the Netherlands over the last 1,000 years. Now, I think no one has a good feeling with this number. I don't, at least. But if you convert it to CO2, it's about slightly over 3 gigatons over the last 1,000 years. And that is equivalent to 0.39 ppmv atmospheric increase. Now, we have, as humans, increased the atmospheric concentration of CO2 with more than 100 ppmv. So it's a relatively small amount. But you have to realize that with land use, our increase is about 10 ppmv. So it's about 4% of the total land use related increase in carbon dioxide in the atmosphere. My final slide is this one. Now we have a longer term story of how this coastal plain captured carbon at first and is now releasing carbon. So on this axis the age, and in the blue line you can see the relative sea level rise in the Dutch coastal plain. Now at some point, 5,000 years ago or slightly later, the peat started to grow above the relative sea level rise. So then we were storing more carbon than we should have had with normal accommodation space creation. And in the end, it says above here, we had 1,000 years ago, we had 6.9 gigatons of carbon stored in the Dutch subsurface in the peat. If we wouldn't have drained the peat then, we may have got 8.6 at some point in time. But instead we drained the peatlands, and then we lowered our carbon stock. This is all emission, and now we have 3.8, so about half of the 6.9 is still left in the subsurface. So half of it is gone, the other half is still here. Of course, the big challenge to combat climate warming is to keep as much as possible of that half that's still there also in the subsurface. Thank you very much.
So are there questions for Gilles? Yes, Pietro. We have room for 2.6 questions, Gilles.
Thank you, Gilles. One question is, why you don't show any direct measurement of CO2 efflux from the peat? Because we can also measure using local chamber, but as well as also micrometeorological station that give us the possibility also to have some more average and wide understanding of the flux, and so in some way calibrate your analysis, indirect analysis.
Yeah, now that's a very good point, and something that we've been working on in the last couple of years, and there are many people here in the room that work on this, to have a new monitoring system for CO2 respiration from peatlands. I didn't show that here, but we could maybe in the next phase. It's important to realize though that the current land subsidence in the Netherlands in the peatlands is about 5 to 6 millimeters per year, and here we have on average 2 millimeters per year. So since the Second World War, when we reparceled the peatland, we had more powerful pumping station, more intensive land use. We also increased the amount of land subsidence. This was why there was a small increase in the end. So if you compare the present day CO2 respiration values, they will also be much higher on average than the average that we had over the last 1,000 years. I think, yeah.
There's time for a small question. Yes, Carol.
Hey, thanks, Gilles. I've always wondered this because I deal with bulk densities and organic matter all the time. When you calculate your organic matter, I guess that the density, is that with the dry mass or the wet mass? And then how is that volume of water that may be removed when it's dried, potentially impacting how those graphs look.
Yeah, it's dry mass only. We only use dried samples to calculate the mass of the organic matter. But it wouldn't impact this graph. Would be the same. And the only thing is that if you have this wide range, that the ones which are on the top, which have a higher organic matter density, they usually have a lower porosity, so they have slightly less water in general, but that's in the porosity which is in the graph. So the total result will be the same. Of course, you cannot use this to see, for instance, the specific storage, or to calculate the specific storage from these in hydrology from these samples. That's impossible. Yeah. Yeah. Thank you.